What if everything you know, the stars in the night sky, the ground beneath your feet, even the air you breathe, could vanish in an instant, not with a bang or a whimper, but with a silent, irreversible blink? It sounds like science fiction, but it's one of the most sobering ideas in modern physics, that our universe might exist in a fragile state known as a false vacuum, a temporary bubble of stability in an otherwise unstable cosmic landscape. Picture living in a beautiful, spacious house, one you've always called home. You walk its halls, cook in its kitchen, sleep safely in its rooms, but what if you suddenly learned that the entire foundation was built on a fault line, and at any moment, without warning, the ground could give way? That's the unsettling possibility physicists are exploring when they talk about the false vacuum. Our reality, as stable and permanent as it feels, might be balancing on the edge of total annihilation. This isn't just wild speculation. It arises from our deepest understanding of the laws that govern the universe, from quantum field theory to the nature of empty space itself. Scientists call it vacuum decay, a chain reaction that could begin at any point in the cosmos and race outward at the speed of light, rewriting the fundamental rules of reality as it expands. There would be no warning, no time to react. One moment, everything is as it's always been. The next, the universe as we know it ceases to exist, replaced by something entirely new and unpredictable. It's a concept that challenges not only our sense of safety but our very understanding of existence. And what's perhaps most remarkable is that this isn't some far-off apocalyptic fantasy. It's a scenario that, according to our best models, could literally happen at any time. So how do we wrap our minds around something so vast, so abstract, yet so deeply personal? In this video, we're going to explore one of the most profound and eerie ideas in all of science, the possibility that we live in a false vacuum, a universe on the brink. We'll break down the science behind this stunning theory in clear, relatable terms, using everyday analogies and thought experiments to make sense of concepts that stretch the imagination. From the nature of cosmic stability to what it would mean for reality itself to unravel, we'll journey together into an idea that forces us to reconsider everything we thought we knew about the cosmos and our place within it. This is more than physics. It's a window into the breathtaking fragility and beauty of existence itself. So let's dive in. To understand this idea of a false vacuum, we need to start with a counterintuitive truth. What we think of as completely empty space isn't empty at all. Even in the deepest void between galaxies, space is not truly nothing. It's filled with a kind of invisible energy field, a fundamental backdrop to reality known as the Higgs Field. This field is everywhere, and it's responsible for giving particles their mass. Without it, the universe as we know it couldn't exist. Electrons would zip around at the speed of light, atoms could never form, and you and I would not be here. The value of this field is like a dial that has been set to a specific number, and that number determines the laws of physics and the behavior of everything in our universe. Now, this is where the false part comes in. Imagine that dial isn't in its final, most comfortable resting position. Instead, it's temporarily stuck in a higher setting. Think of it like a ball resting in a small valley partway up a large mountain. From the ball's perspective, it's in a stable spot. It's not moving, it feels secure. But it's not at the true bottom of the mountain. If something were to give that ball enough of a nudge to get it over the valley's ridge, it would tumble all the way down to the base of the mountain, a much lower and more stable state of energy. Our universe might be that ball. The valley it's sitting in represents our current, seemingly stable vacuum. The true bottom of the mountain represents a different, lower energy vacuum state. This is the false vacuum scenario. Our universe is stable for now, but it's not in its most stable possible form. It's metastable, which is a scientific term for temporarily stable. A fantastic analogy for this is supercooled water. You can take very pure water and carefully cool it below its freezing point to, say, -10 degrees Celsius, and it will still remain a liquid. It looks perfectly calm and stable in its glass, but this state is incredibly fragile. The slightest disturbance, a tiny vibration, a speck of dust, can trigger an instantaneous and dramatic phase transition. In a flash, the entire volume of water will explosively freeze solid. Our universe might be in a similar supercooled state. It appears stable, but it could be sitting in that precarious false valley waiting for a trigger. In the cosmic sense, that trigger could be a random quantum fluctuation, a tiny, spontaneous burst of energy that can happen anywhere at any time. If this fluctuation provides enough energy to push the Higgs field over its metaphorical ridge, it would create a tiny bubble of this new, true vacuum. The laws of physics inside that bubble would be completely different. This bubble would then expand in all directions at the speed of light, fundamentally altering the fabric of reality as it goes. There would be no way to see it coming and no way to outrun it. One moment our universe exists, the next it is rewritten into something unrecognizable. This isn't an explosion of matter, it's a wave of change, redefining the very constants of nature from which not even light can escape. Now, to really grasp how this precarious situation could be possible, we need to get to know the star of the show, the Higgs field. This isn't some abstract, faraway concept. It's an invisible energy field that permeates every single cubic centimeter of the universe, from the vast emptiness between stars to the space right in front of your eyes. Its most famous job is to give other particles their mass. Think of it like a cosmic vat of molasses that certain particles have to wade through. Particles that interact strongly with this field, like quarks and electrons, move slower and gain what we perceive as mass. Particles that don't interact with it, like photons of light, zip through at the universe's ultimate speed limit. This mechanism is a cornerstone of the standard model of particle physics, our best and most rigorously tested map of the fundamental particles and forces that make up everything. It's a theory that has been proven correct time and time again in massive experiments like the Large Hadron Collider, where the Higgs boson, the observable quantum excitation of the Higgs field, was famously discovered. But here's the twist that leads us to the false vacuum idea. The standard model doesn't just tell us the field exists. Its complex mathematics also suggests what its most stable, lowest energy state should be. And there's a compelling argument that the value we observe it at today might not be that true bottom. It might be a local minimum, a stable-looking resting point that isn't the global, absolute minimum. This is where the valley and mountain metaphor becomes so powerful. Picture an entire landscape of possible energy states for the universe. Our current universe isn't sitting at the very bottom of the deepest valley. Instead, it's sitting in a higher valley on the side of a much, much deeper crater. From our perspective inside this valley, everything seems fine. The ground is flat, the grass is green, and the laws of physics are constant. We have no reason to suspect we aren't at the very bottom, but over the ridge of our valley lies a sheer cliff, a steep drop down to a far more stable state of existence. This state of being metastable temporarily but not eternally stable is a perfectly valid and allowed solution within the equations of the standard model. The math doesn't force our universe to be in the absolute lowest energy state. It merely allows for it. The unsettling part is that if our particular valley is indeed just a local minimum, then the potential exists for a quantum tunneling event. This is a bizarre but very real phenomenon where, thanks to the probabilistic rules of quantum mechanics, a system can spontaneously transition to a lower energy state without having to first climb the energy hill in between. It's as if that ball in the valley could suddenly, randomly, find itself on the other side of the ridge without anyone pushing it, simply due to the fuzzy, unpredictable nature of reality at the smallest scales. If such an event occurred anywhere in the universe for the Higgs field, it would create that catastrophic bubble of true vacuum, initiating a chain reaction that would change everything. So if our universe is indeed perched in this precarious false valley, what could possibly push it over the edge? The answer lies in one of the most bizarre and counterintuitive principles in all of science: quantum tunneling. This isn't science fiction. It's a well-documented phenomenon that happens all the time in the subatomic world, and it could be the silent, invisible mechanism that ultimately unravels our reality. To understand quantum tunneling, we first need to grasp a fundamental rule from the classical world of physics. Imagine a ball rolling up a hill. If the ball doesn't have enough kinetic energy to reach the top, it will roll back down. It's trapped in the valley. This is how our everyday world works, but in the quantum realm, the rules are different. Particles like electrons don't behave like tiny billiard balls. They behave more like spread-out waves of probability. This wave-like nature means a particle isn't in just one specific place at one time. Instead, it has a certain probability of being found at any point within its wave function. Now picture that same hill, but now it's an energy barrier. A particle doesn't have the energy to go over the top of this barrier. According to classical physics, it should be completely trapped. But because of its wave-like nature, there's a small yet finite probability that the particle will simply appear on the other side of the barrier, as if it had tunneled through an invisible passage. It doesn't break the energy barrier, it doesn't climb over it, it just has a chance to spontaneously be there. This isn't a theory, it's a proven fact that is essential for how the sun shines. Proton fusion at the heart of our star relies on quantum tunneling to overcome the immense electrical repulsion between positively charged nuclei. Without this process, stars wouldn't ignite, and life as we know it wouldn't exist. Apply this same principle to the Higgs field and our mountain valley metaphor. The ridge surrounding our valley is an energy barrier. For the field to transition to the true vacuum, it would need a massive jolt of energy to push it up and over that ridge. But quantum tunneling offers another path, one that requires no outside influence whatsoever. Through a random quantum fluctuation, the field could, with incredibly low probability, simply tunnel through that energy barrier. It wouldn't need to be pushed over the top. It would just suddenly find itself on the other side, in that steeper slope leading down to the true vacuum state. This is the ultimate cosmic Russian roulette. The trigger isn't a meteor impact or a scientist in a lab making a mistake. The trigger is the random, unpredictable nature of reality itself at the most fundamental level. It could happen anywhere at any time. A tiny, spontaneous quantum event in the empty space between galaxies or even in the air in front of you could be the genesis point. This event would create a microscopic bubble of this new, true vacuum, and the laws of physics inside that bubble would be utterly alien. The moment that bubble forms, the rules change. The most unsettling part is the silence and the speed. There is no warning. This bubble would expand in all directions at the speed of light. You cannot see it coming because the signal of its approach, the light itself, is traveling at the same speed as the wall of change. 1 nanosecond you exist in our familiar universe. The next nanosecond, the wavefront passes through you, and every fundamental law that governs your atoms is rewritten. Molecules disintegrate, atomic bonds cease to have meaning, and the very concept of you is erased in an instant, replaced by a new reality operating under a completely different set of physical constants. It's not an explosion, it's a transformation so total and so swift that from our perspective, it would be indistinguishable from instantaneous oblivion. This wave of fundamental change, this bubble of true vacuum, would be the most dramatic and final event in the history of our cosmos. To visualize its propagation, picture a single, impossibly tiny point in space. Perhaps it forms in the deep void between galaxies, or maybe shockingly close, right here in our solar system. At the moment of its genesis, this point becomes the epicenter of a new reality. The sphere of true vacuum begins to expand from this point in all directions, not as a physical explosion of force, but as a wave of reconfiguration. The boundary of this sphere is a wall of pure transformation, a shockwave of new physics moving outward at the ultimate cosmic speed limit, the speed of light. The most terrifying aspect of this event is its absolute silence and invisibility. Because the bubble expands at light speed, there is no possible warning. Information itself carried by light or any other signal cannot outrun the leading edge of this change. If the bubble began its journey from a distant star, we would have no way of knowing it was coming. The first hint of its arrival would be the moment it reached us, rewriting the laws of our local reality in the same instant we perceive its existence. It would be a sight we could never see, a sound we could never hear. Our entire observable universe from our perspective would simply cease in a single, uniform moment. As this spherical wall of new physics passes through a region of space, it doesn't smash or incinerate matter in a conventional sense. Its effect is far more profound and absolute. It instantly alters the fundamental constants that govern particle interactions. The strength of forces, the masses of particles, the very rules of chemistry, everything is reset to a new set of values dictated by the true vacuum's lower energy state. In this new environment, the atomic structures that form the basis of our reality become impossible. The delicate balance of forces that holds a nucleus together, that binds electrons to atoms, and that allows molecules to form, simply vanishes. Atoms would disintegrate in a flash. The complex structures of protons and neutrons, built from quarks held together by the strong nuclear force, would instantly come apart as those binding forces are redefined or eliminated. Electrons would either be granted a new, different mass or cease to interact with matter altogether. Every molecule in your body, in the air, in the planets and the stars, would unravel into a soup of fundamental particles that no longer know how to assemble into anything recognizable. The universe wouldn't be filled with debris. It would be filled with a new, alien state of matter operating under a completely different and likely much simpler set of rules. The rich complexity born from our specific physical constants would be erased, replaced by a bland and sterile reality where the concept of a star, a planet, or life is not just impossible but unimaginable. It is the ultimate, unstoppable end of everything we have ever known or could ever know. This leads us to one of the most chilling questions we can ask. Could this process have already begun? Is it possible that somewhere in the vast expanse of the cosmos, a bubble of true vacuum has already been born, and its sphere of annihilation is already expanding, racing toward us at the speed of light at this very moment? The unsettling answer, rooted in the hard logic of physics, is yes. It is not only possible, but if our universe is indeed in a false vacuum state, it is statistically inevitable over a long enough timeline. The trigger event, a random quantum fluctuation, has a non-zero probability of happening anywhere at any time. Given the immense size and age of the universe, the dice have been rolled an almost infinite number of times. But if this bubble is expanding at light speed, and light is the fastest thing in the universe, how could we ever know it's coming? The answer lies in a fundamental concept in physics known as the light cone. Think of any event, a star exploding, a bubble of true vacuum forming, as a single point in the vast fabric of space-time. The future light cone of that event is the three-dimensional volume of space that can possibly be affected by it, defined by the maximum distance light could have traveled since the event occurred. Nothing, not even information, can travel faster than light. This means that for an observer on Earth, we can only be aware of events whose light cones have already reached us. We are forever locked in the now of our own perception, unable to see anything until the light from it finally arrives. Now apply this to our vacuum decay bubble. Imagine it formed 50 million years ago in a galaxy 50 million light years away. From the moment of its creation, two things begin expanding outward at the exact same speed: the sphere of the bubble itself rewriting reality, and the sphere of light carrying the information that this event has happened. Crucially, they are expanding at the same velocity. The wall of change and the first photon of light that could warn us of its coming are traveling neck and neck. There is no way for a signal to get ahead of the bubble's boundary to alert us. The very first warning we would ever receive that our universe was being erased would be the moment the bubble's wall physically reached our planet. Our entire solar system would be transformed into a new state of reality in the same instant we would have seen the light from the bubble's origin point. For us, the end of everything would be completely simultaneous with its only possible announcement. This means we are living in a state of profound cosmic uncertainty. The event could have happened a minute ago in a distant solar system, and we would have no way of knowing. It could have happened a billion years ago on the other side of the galaxy, and the wall of transformation could be just days or even seconds away from Earth. We are utterly blind to it until the very moment it arrives. There is no scientific instrument we could build, no watchtower we could construct that would grant us even a fraction of a second's advance notice. This isn't a failure of our technology, it's a fundamental limit imposed by the laws of physics themselves. The universe does not allow for spoilers for its own potential destruction. Given the immense energies involved, it's natural to wonder if we ourselves could accidentally be the ones to push the universe over the edge. Could a machine built by humans like the Large Hadron Collider create the right conditions to trigger this transition? The LHC smashes protons together at velocities incredibly close to the speed of light, recreating for a fleeting instant the kind of energy densities that existed just after the Big Bang. The goal is to uncover new particles and forces to probe the very fabric of reality, and in doing so, it creates microscopic fireballs of extreme energy. The question is whether such a concentrated burst could provide that critical nudge for the Higgs field, creating a bubble of true vacuum in the heart of the detector. Scientists have thoroughly investigated this possibility, and the consensus is a resounding and reassuring no. The energies produced by the LHC, while monumental by human standards, are utterly insignificant on a cosmic scale. The universe routinely conducts far more violent experiments without any sign of vacuum decay. For billions of years, cosmic rays, high-energy protons, and atomic nuclei racing through space have been colliding with atmospheres, planets, and even each other at energies far exceeding anything we can generate in our laboratories. Some of these cosmic rays carry energies millions of times greater than what the LHC can produce. If such high-energy collisions were enough to destabilize the vacuum, it would have happened naturally eons ago, somewhere in the cosmos. The fact that we are still here and that the universe appears stable after 13.8 billion years of these natural particle accelerators is a strong indication that our colliders pose no threat. The energy barrier protecting our false vacuum, if it exists, is almost certainly too high to be overcome by any event we can currently create or observe. But what about events far beyond our own capabilities? The cosmos is a theater of immensely powerful phenomena that make our particle colliders look like toys. Neutron star mergers, hypernova, and the environments around supermassive black holes all generate conditions of mind-boggling energy and density. Could one of these cosmic cataclysms serve as a potential trigger? It's a more complex question. While these events are far more energetic, they are also messy and diffuse compared to the precisely controlled, microscopic focus of a quantum tunneling event. The energy required isn't just about raw power, it's about applying that energy in the right way to the right field at a quantum level. Most physicists believe that even these spectacular astrophysical events lack the specific, concentrated punch needed to overcome the energy barrier. The primary catalyst remains the spontaneous, random quantum fluctuation, a ghost in the machine of reality that requires no outside cause whatsoever. This leads to one of the most speculative yet fascinating possibilities: the role of intelligence. Could a sufficiently advanced civilization, one that has mastered physics to a degree we can scarcely imagine, inadvertently or deliberately manipulate the fundamental fields of the universe? Imagine a technology millions of years beyond our own, capable of engineering space-time itself or creating stable wormholes. The energy requirements for such feats would be astronomical, perhaps involving harnessing the power of entire stars. In the process of executing such a grand experiment, could they create a local configuration of energy that exceeds the critical threshold? It's a staple of science fiction, but it rests on the edge of theoretical plausibility. If the universe allows for such technologies, then it might also allow for a catastrophic mistake. A civilization, in its quest for ultimate knowledge or power, might accidentally become the agent of its own and everyone else's demise. This idea transforms the false vacuum from a purely natural phenomenon into a potential risk of cosmic sociology, a reminder that the greatest dangers in the universe might not come from the cold indifference of nature, but from the ambitious and perhaps reckless application of knowledge by its inhabitants. Ultimately, the most probable trigger remains the most impersonal and democratic: a random quantum fluctuation. This is the universe playing a game of chance with itself on a cosmic scale. At any moment, in any location, the dice could come up the wrong number. The unsettling truth is that the mechanism that could end all existence is the same fundamental randomness that allows particles to pop in and out of existence everywhere all the time. It's the default background hum of reality, and within that hum lies a seed of potential total transformation. This shifts the discussion from what could cause it to a deeper acceptance of its inherent unpredictability. We are not looking for a specific catalyst to watch out for, but rather grappling with a fundamental property of the universe itself, one that is both creative and potentially destructively neutral. Given the sheer scale of the potential catastrophe, it's only natural that the idea of vacuum decay would eventually leap from the pages of physics journals and into the public consciousness, sparking genuine fear and controversy. This came to a head in the years leading up to the launch of the most powerful scientific instrument ever built, the Large Hadron Collider. As the LHC prepared to smash protons together at unprecedented energies, a small but vocal group of concerned individuals asked a terrifying question: could this machine, designed to uncover the secrets of the universe, accidentally be the one to destroy it? The theoretical possibility, however remote, was enough to fuel a very public and dramatic debate, one that even found its way into a courtroom. The fears were not born out of simple paranoia, but from a layperson's attempt to engage with complex theoretical physics. The logic seemed frighteningly straightforward. The LHC was designed to create conditions not seen since the first moments after the Big Bang, concentrating immense energy into a vanishingly small space. If our universe truly is a false vacuum teetering on the edge of stability, then such a massive concentration of energy could, in theory, provide the nudge needed to push the Higgs field over its energy barrier. The thought experiment was terrifying, a machine built by humanity becoming the catalyst for the end of all existence. This concern was amplified by media headlines that often prioritized sensationalism over scientific nuance, creating a perfect storm of public anxiety. This anxiety manifested in a very tangible way. In 2008, as the LHC was nearing its operational debut, a lawsuit was filed in the United States District Court for the District of Hawaii. The plaintiffs sought a temporary restraining order to halt the collider's activation, citing fears that it could create a cataclysm, whether a planet-swallowing black hole or, more relevant to our topic, a bubble of true vacuum. The lawsuit argued that CERN, the European organization that operates the LHC, had not provided a sufficient safety assessment for these exotic, worst-case scenarios. It was a surreal moment where the frontiers of theoretical cosmology collided with the practical world of legal injunctions and government oversight. While the case was ultimately dismissed, it highlighted a profound cultural moment, the deep-seated fear that accompanies humanity's reach for ultimate knowledge. So, how did the vast majority of the physics community respond to these fears? With a resounding and carefully reasoned dismissal, not born out of arrogance, but from a deep understanding of the evidence written across the cosmos itself. Their argument rests on a simple and powerful piece of observational data. The universe is old and it is violent. For over 13 billion years, nature has been conducting its own version of LHC experiments on a scale we can barely comprehend. Cosmic rays, high-energy protons and atomic nuclei from deep space are constantly bombarding planets, moons, and each other. The energies reached in these natural collisions can be staggeringly higher than anything the LHC can achieve. In fact, scientists observe cosmic ray collisions with energies over 1 million times greater than those produced inside the LHC. If it were possible for a high-energy particle collision to create a catastrophic vacuum decay event, it would have already happened. A natural cosmic ray would have triggered it somewhere in the universe at some point in the last 13.8 billion years. The fact that we are still here and that we observe a stable and consistent universe stretching as far as our telescopes can see is the most compelling evidence that the LHC poses no such threat. The safety argument isn't based on a hunch, it's based on empirical observation. The universe has already stress-tested its own stability under conditions far more extreme than anything we can create in Geneva, and it has remained intact. Furthermore, physicists emphasize the sheer mathematical improbability of such an event. The calculations governing quantum tunneling and vacuum decay involve probabilities so infinitesimally small they are effectively zero for any human timescale. It's a numbers game played with the entire universe. While the probability of a spontaneous quantum fluctuation causing decay might be non-zero over trillions of years, the probability of a human-made machine causing it is dwarfed into irrelevance by the constant, natural particle collisions happening all around us every second. The scientific consensus is clear and unanimous. The LHC is not a danger. It is a tool for discovery, peering into the fundamental laws that govern our existence, and the risk of it unraveling those very laws is mathematically negligible. The real story isn't one of danger, but of the incredible and resilient stability of the cosmic order we call home. Even with the overwhelming unlikelihood and the silent, invisible nature of a vacuum decay event, the human drive to understand and observe is relentless. We are not content to simply accept a theoretical doom. We want to look for evidence, to scan the heavens for any sign that this process might have happened elsewhere. So, how could astronomers possibly search for the ghost of a universe that has been erased? If a bubble of true vacuum expands at light speed, wiping out all information in its path, what signature could it possibly leave behind for us to detect? The answer lies not in looking for the void itself, but in searching for its potential aftermath and for the faint, theoretical echoes it might produce at the very moment of its birth. The most promising place to search isn't within the bubble, but at its very beginning. Physicists theorize that the instant a bubble of true vacuum forms through quantum tunneling, the event would not be completely silent. The transition from one vacuum state to another would release an enormous amount of energy in a spectacular burst of radiation. This wouldn't be a conventional explosion. It would be a fundamental release of energy as the field tumbles down its energy landscape to a more stable state. This burst would theoretically produce a very specific and potentially detectable signature across the electromagnetic spectrum, from radio waves to gamma rays. Astronomers are constantly monitoring the sky for transient events, sudden, short-lived flashes of energy that appear and then vanish. Most are explained by known phenomena like supernova or merging neutron stars. But what if we detected a burst of energy that defies all known classifications? one that doesn't match the profile of any star, any collision, or any explosion we've ever catalogued. Such an anomalous event, especially if it were point-like and vanished without a trace, could be a candidate for something far more exotic, the birth cry of a new vacuum. Another intriguing possibility involves looking for the structural aftermath. Imagine a scenario where a vacuum decay event occurred not in our recent past, but billions of years ago in a distant galaxy. The sphere of transformation would have long since passed through that region, leaving in its wake a vast volume of space operating under a new set of physical laws. From our vantage point, what would that region look like? It might appear as a mysterious void in the cosmos, a place where the normal structures of the universe, galaxies, stars, and nebulae are completely absent. But not just any void, this would be a void of a different character. The physics inside it would no longer support the complex nuclear reactions that power stars, so it would be utterly dark. It wouldn't just be empty, it would be inactive on a fundamental level. Astronomers have indeed mapped enormous voids in the large-scale structure of the universe, but these are generally explained by the gravitational evolution of the cosmos. The search is for a void that is an absolute outlier, one that appears too perfect, too empty, and too geometrically spherical to be explained by conventional cosmology. Finding such a perfect cosmic blank spot could be a hint that we are looking at the scar tissue left by a vacuum decay event that rewrote reality eons ago. The search also extends to the very boundaries of these theoretical spheres. The wall of the bubble itself, the shockwave of changing physics, is another potential source of a signal. As this wall moves through space, it might interact with the plasma and matter in the interstellar medium in complex ways. Some theories suggest this interaction could generate a faint, shell-like emission of radiation that might be detectable as a strange, circular anomaly in the sky. It would be like seeing the ripple from a stone thrown into a pond, but on a universal scale. Identifying such a structure would require painstaking analysis of deep-field astronomical surveys, looking for subtle imperfections or rings of energy that have no clear origin. It's a needle in a haystack search, but the potential payoff evidence of a fundamental reshaping of reality is unimaginably profound. This entire endeavor highlights a beautiful and paradoxical aspect of modern science. We are using the stable, consistent laws of physics within our current vacuum to search for evidence that those very laws are not universal and can be broken. Our telescopes, our detectors, and our theories all operate under the assumption that the constants of nature are constant, yet we are deploying them to find proof that they are not. It's a cosmic detective story where the clue is the absence of the normal rules. While no conclusive evidence for vacuum decay has ever been found, the very act of looking transforms the concept from a purely philosophical terror into a tangible scientific question. We are not just waiting in the dark, we are actively probing the universe's deepest mysteries, testing the limits of our understanding and searching for any sign, however faint, that the cosmos is even stranger and more dynamic than we ever dreamed. To truly appreciate the scale of this idea, we need to zoom out from our single universe and consider an even grander canvas, the multiverse. The concept of vacuum decay isn't just a standalone doomsday scenario. It's a pivotal chapter in a much larger story of cosmic creation and destruction, a process theorists call eternal inflation. This framework suggests our entire universe, with its hundreds of billions of galaxies, might itself be just one bubble in a frothing, infinite sea of other universes, each with its own unique set of physical laws. Think of the multiverse not as a collection of separate realms, but as an endlessly bubbling cauldron of space-time. Imagine an infinite hyper-energy background, a primordial soup of unstable space that is constantly and exponentially expanding. This is the inflattened field, a cousin to the Higgs field, forever in a state of high-energy frenzy. Within this raging sea, random quantum fluctuations can cause tiny pockets of this inflated field to suddenly lose energy, collapsing down into a stable, low-energy state. Each one of these collapsing pockets is a Big Bang event. It pinches off from the inflating background and begins expanding at its own pace, creating an entire new universe within the bubble, complete with its own randomly determined laws of physics. In this view, our universe isn't a one-off creation. It's just one bubble that happened to form in the right way, in the right place, with the right constants to allow for our existence. This is where the false vacuum finds its profound context. In this eternal inflation scenario, the death of one universe is often the birth of another. The very same process that might spell our end vacuum decay could be the engine of creation elsewhere. If our universe is in a false vacuum, then somewhere out there in the infinite inflating background, a quantum fluctuation might have already triggered the formation of a bubble of our true vacuum. That bubble would then expand at light speed, not as a wave of destruction, but as a wave of genesis, rewriting the laws of physics within its sphere into a new, stable state. For the inhabitants of that doomed universe, it's the end of everything. But from the multiverse perspective, it's simply a cosmic turnover, the death of an old universe making way for the birth of a new one with different properties. Our potential annihilation is just a routine recycling event on a scale so vast it defies human comprehension. This paints a picture of a dynamic and violent multiverse, a cosmos in a state of permanent flux. Universes are constantly popping into existence through the process of bubble nucleation, each one a separate experiment in physics. Most of these universes would be stillborn, their physical constants perhaps not allowing for atoms or forces or any complex structures at all. They would inflate, exist as barren voids, and potentially decay away again. A rare few, like ours, would hit the cosmic jackpot, landing on a set of laws that allow for galaxies, stars, planets, and life. But even these lucky ones are not permanent. Their stability is only temporary, a precarious balance that could be upset at any moment by a random quantum event, resetting the experiment and making room for new possibilities in the infinite fractal of existence. We are not living in a unique, sacred cosmos, but in one that is both miraculous and utterly commonplace, a single leaf on an infinitely branching tree that is forever growing and dying simultaneously. So when could this actually happen? The answer to that question is perhaps the most dizzying and unsettling part of the entire false vacuum scenario, because it lives at the intersection of precise mathematics and absolute, profound uncertainty. The calculations physicists use to estimate the probability of vacuum decay are not based on guesswork. They are derived from the complex equations of quantum field theory and our measured values of particle masses and forces. These equations can, in principle, spit out a number, the half-life of our metastable universe. That number represents the time after which there is a 50% chance that a decay event has occurred somewhere in the observable universe. The results of these calculations are so vast they defy human intuition. Some models, using our best current data, suggest the half-life of our universe could be on the order of 10 to the power of 100 years. That's a 1 followed by 100 zeros. To call that number astronomical would be a comical understatement. It is billions upon billions of times longer than the current age of the universe, which is a mere 13.8 billion years old. On this timescale, the entire current lifespan of our cosmos from the Big Bang to today is less than the blink of an eye, an infinitesimal flash in an ocean of time so deep it has no shore. If this math is correct, we are not just safe for our lifetimes, we are safe for a duration so long that all the stars in the sky will have burned out, galaxies will have drifted apart into darkness, and even black holes will have evaporated away due to Hawking radiation, all long before the coin flip of vacuum decay is even remotely likely to have landed on tails. But, and this is a crucial, but these calculations are built on a foundation of assumptions and measurements that are not yet absolute. our understanding of physics is incomplete. The Standard Model is incredibly successful, but it does not include gravity, and it may well be superseded by a more complete theory like string theory. The estimated stability of the vacuum is exquisitely sensitive to the precise mass of the top quark, the heaviest of all known fundamental particles. A tiny adjustment to that mass, well within the current margin of error of our measurements, could dramatically shift the probability. Some plausible calculations, using slightly different values or interpretations, suggest a much shorter half-life, perhaps as short as 10 to the power of 60 years. While that is still an unimaginably long time, it highlights the fragility of our certainty. We are balancing these cosmic probabilities on the head of a pin, on the precise value of a single particle's mass. This leads us to the true heart of the unease. The mathematics does not rule out the possibility that the half-life is not trillions of years but could be much, much shorter. In fact, from a purely probabilistic standpoint, the most likely time for a random event with a constant, minuscule probability to occur is not in the far future, but literally at any moment. Think of it like this: if you buy a single lottery ticket, your odds of winning the jackpot are astronomically low. But if you do win, the most likely time for that win is on the very first draw you enter. The odds don't get better the longer you play. Each draw is an independent event with the same tiny chance. Vacuum decay is the ultimate quantum lottery, and every single instant that passes is another independent drawing. The universe has already held 13.8 billion losing tickets, but the odds for the next second are exactly the same as they were for the second after the Big Bang, and exactly the same as they will be a trillion years from now. This is why physicists soberly state that, according to the theory, it could happen in the next second or it may never happen at all. There is no building up to it. There is only the relentless, unchanging, and infinitesimal probability attached to every tiny fragment of spacetime. This absolute unpredictability is what makes the concept so existentially jarring. We are accustomed to threats that give warnings. A hurricane appears on satellite days in advance. An asteroid's path can be calculated years before a potential impact. Even the death of our sun is an event scheduled for billions of years in the future. But vacuum decay offers no such comfort. It is the ultimate ambush, a threat with no precursor, no sign, and no timeline. It democratizes time itself, placing the final second of the universe on the same probabilistic footing as any other second. This means we are living in a state of permanent, low-probability peril, a background hum of potential oblivion that is woven into the very fabric of reality. We are forced to confront the fact that our continued existence is not guaranteed by the laws of physics, but is instead a contingent and ongoing statistical anomaly, a run of good luck on a cosmic scale that could end at any time for no reason whatsoever. Yet if our own actions are almost certainly not a danger, the idea itself opens a door to a deeper philosophical question about humanity's ultimate role in the cosmos. Are we merely passive passengers on this ride through a potentially metastable universe, or could we, in the far distant future, become active participants in its preservation? This shifts the discussion from a simple question of cause to a breathtaking speculation about responsibility and cosmic engineering on a scale that dwarfs anything we can currently conceive. First, let's entertain the far-fetched but fascinating scenario of causation. While our current technology is harmless, what about a civilization 1 million or 1 billion years more advanced than our own? The energy requirements to manipulate the fundamental fields of the universe would be godlike, perhaps involving harnessing the entire energy output of stars or even galaxies. In the process of running an experiment of such unimaginable scale, perhaps trying to create a stable wormhole, unify all fundamental forces, or even create a new universe in a lab, could such a civilization inadvertently create the precise conditions needed to destabilize the false vacuum? It's a chilling thought that the pinnacle of intelligence and knowledge could accidentally become the instrument of ultimate destruction. This transforms the false vacuum from a natural phenomenon into a potential risk of cosmic sociology, a reminder that the greatest existential threats might not come from outside, but from within the ambitious, curious mind itself. Now flip that terrifying possibility on its head. If a future civilization could potentially pose such a risk, could it also learn to mitigate it? This is where the conversation moves from despair to a kind of awe-inspiring hope. The first and most crucial step would be detection. A society that has mastered physics might develop sensors of unimaginable sensitivity, not just looking for the aftermath of a decay event, but perhaps monitoring the stability of the Higgs field itself across vast regions of space. They might deploy a galaxy-spanning network of observatories designed to pick up the faintest precursor signals, the quantum whispers that might hint at an impending transition, giving them an advance warning that the laws of physics currently deny us. With advanced warning, the next step is prevention. How do you stop a process that is triggered by a random quantum fluctuation? You wouldn't fight the fluctuation itself. That's like trying to stop the wind. Instead, you would work to change the underlying landscape. The goal would be to stabilize the valley, to gently lower the entire energy state of our local vacuum so that it becomes the true global minimum, eliminating the dangerous cliff edge altogether. The energy required to perform such cosmic landscaping is beyond comprehension. It might involve generating counter fields or creating precise concentrations of energy at specific points in spacetime to gradually nudge the entire field into a safer configuration. This wouldn't be building a dam, it would be gently repositioning the entire mountain range of reality itself. The sheer scale of such a project hints at a future where humanity, or any intelligent species that survives long enough, evolves from being inhabitants of the universe to its stewards. Our responsibility would expand from caring for a single planet to actively maintaining the stability of the cosmos that allows us to exist. This is perhaps the ultimate expression of intelligence, not just understanding the laws of nature, but learning to gently tend to them, ensuring the continuity of existence for countless generations and civilizations yet to come. It redefines our potential purpose, suggesting that the long-term goal of a technological civilization might not be conquest or consumption, but the quiet, noble work of cosmic preservation. This brings us to a profound and deeply human question that sits at the heart of this entire discussion. Should we even be researching this? Is there a moral cost to peering into the abyss and discovering a potential doom that we are powerless to prevent? On one hand, this knowledge can feel like a burden, a source of existential anxiety that casts a shadow over our daily lives. Why spend time and resources contemplating a hypothetical end that offers no warning and, by all current understanding, no possible escape? Isn't this just a recipe for fear, a distraction from the tangible problems we face here on Earth? These are valid and weighty concerns. There is an argument to be made that some truths, especially those that can induce a sense of helplessness, might be better left unexplored. Yet the counterargument is equally powerful and speaks to the very core of the scientific endeavor. Ignorance has never been an effective shield against danger. Throughout history, humanity has progressed by staring down its fears and seeking to understand them, no matter how terrifying they may be. We learned about the paths of asteroids not to frighten ourselves, but to one day develop the capability to deflect them. We study virology and epidemiology not to panic about pandemics, but to create vaccines and treatments that save millions of lives. The act of investigating a threat is the first and most crucial step toward eventually mitigating it. To refuse to look into the void is to guarantee that if there is something lurking there, we will be completely unprepared. Awareness, even of a terrifying possibility, is the bedrock of preparedness. It sparks the curiosity and ingenuity that could one day lead to a solution we cannot even conceive of today. this research also serves a vital philosophical purpose. Understanding the potential fragility of our existence doesn't have to be a source of despair. It can be a powerful catalyst for meaning. The possibility, however remote, that everything could end in an instant throws the incredible improbability and beauty of our current reality into stark relief. It underscores that the universe is not a static, permanent backdrop, but a dynamic and astonishingly rare experiment. This knowledge can fuel a deeper appreciation for the fleeting moment we have, encouraging us to value our connections, our achievements, and our planet with greater intensity. It transforms our perspective from one of passive existence to active, purposeful engagement with the precious time we are given. The specter of vacuum decay, in a strange way, can make life feel more vivid and valuable, not less. Ultimately, the ethical path forward isn't to hide from this knowledge, but to integrate it responsibly into our worldview. The goal of this research isn't to spread alarm, but to pursue clarity. Scientists are not doomsayers, they are cartographers, meticulously mapping the landscape of reality, including its potential cliffs and pitfalls. This mapping is an act of profound responsibility. It is the work of a species that is growing up, graduating from only worrying about local threats to beginning to consider its long-term survival on a cosmic scale. While the risk may be unimaginably small and the solution beyond our current grasp, the simple act of looking, of asking the question, is a testament to human curiosity and resilience. It is a declaration that we would rather face a difficult truth than comfort ourselves with a pleasant fiction, trusting that in the long run, the pursuit of knowledge, no matter how unsettling, is the only way to secure any future at all. However, for all its mathematical elegance and sobering implications, the false vacuum decay scenario is far from a settled fact. It remains a compelling theoretical possibility, but it is not the only game in town. A significant and growing body of thought within the physics community argues for a much more comforting conclusion, that we are, in fact, living in the true vacuum, the absolute lowest energy state, and our universe is fundamentally stable. This perspective isn't based on wishful thinking, but on increasingly refined calculations and a deeper reading of the same laws that gave rise to the scary idea in the first place. The entire false vacuum premise hinges on a specific interpretation of the Higgs potential, the energy landscape that defines its stability. Early calculations, using the best data available at the time, did indeed suggest that the mass of the top quark and the mass of the Higgs boson itself could place our universe in that precarious metastable valley. But physics is a living science, and our measurements have gotten dramatically more precise. The discovery of the Higgs boson in 2012 was a watershed moment, giving us a critical anchor point. Subsequent years of data collection at the Large Hadron Collider have pinned down the properties of both the Higgs and the top quark with incredible accuracy. When these new, sharper numbers are plugged into the equations, something interesting happens. The landscape of the Higgs potential changes shape. That deep, dangerous cliff beyond our valley begins to shrink. In some of the most recent and sophisticated models, it vanishes altogether. The valley floor we're sitting on gently slopes down until it becomes the true global minimum. There is no lower state to fall into because we are already at the bottom. This recalculation is bolstered by considering the influence of other forces and particles that were left out of the simpler early models. Our universe isn't just governed by the Higgs field in isolation. It's a complex tapestry woven from multiple quantum fields, all interacting with each other in ways that can profoundly affect the overall stability picture. When physicists incorporate the full spectrum of known particles and forces into their models, accounting for the subtle gravitational effects at play or the influence of other speculative fields, the resulting cosmic landscape often looks far more secure. It's like realizing that the mountain our valley is on isn't standing alone, but is part of a much larger and more supportive mountain range. The presence of these other features can completely alter the stability calculation, effectively building a sturdy wall that prevents any catastrophic rolling away. Beyond pure theory, there's also a powerful argument from observation, often called the argument from actual existence. The universe is ancient, roughly 13.8 billion years old. In that vast expanse of time, it has been continuously bombarded by ultra-high-energy cosmic rays and witnessed countless violent astrophysical events. If the quantum dice were ever going to land on the unlucky number that triggers vacuum decay, the odds suggest it should have happened at least once by now. The fact that we are here to ponder the question is itself a form of evidence. It's a cosmic version of anthropic reasoning. If the universe were inherently unstable, we wouldn't be around to observe it. Our very existence as conscious observers in a complex, structured cosmos implies a fundamental level of stability that has persisted for billions of years. This isn't a proof, but it's a strong circumstantial clue that the laws of physics are not teetering on a knife's edge. This more optimistic view doesn't just offer emotional comfort, it opens the door to a more profound and perhaps more beautiful understanding of our cosmos. It suggests that the laws of physics we observe are not a temporary and accidental arrangement, but could be the only possible self-consistent set of laws. In this view, the universe isn't metastable, it is fine-tuned for longevity. The constants are what they are because they must be, resulting in a reality that is robust, resilient, and destined to endure in its current form far into the future. This perspective shifts our role from temporary tenants in a fragile bubble to permanent citizens of a stable and enduring cosmos, a universe that is not on the brink, but is instead a mature and settled home, one that has passed its most turbulent phases and settled into a long, stable adulthood. While the mystery of why the constants have the values they do remains, the answer may point less to random chance and more to a deep, yet to be understood necessity woven into the fabric of existence itself. This strange intersection of quantum uncertainty and cosmic stability brings us to one of the most debated and profound puzzles in all of science, the quantum measurement problem. At its heart, this is the question of why the fuzzy, probabilistic world of quantum possibilities seems to snap into a single, definite reality the moment we observe it. An electron exists in a cloud of potential positions until a measurement forces it to choose one. This act of observation, this collapse of the wave function, is central to quantum theory, yet its mechanism remains utterly mysterious. Some interpretations suggest it requires a conscious observer placing the human mind or any mind in a bizarrely privileged position in the universe. Now connect that staggering idea back to vacuum decay. The trigger for cosmic annihilation is a random quantum fluctuation, a tiny, spontaneous event born from the same probabilistic soup. If conscious observation can indeed influence the outcome of a quantum event in a lab, could it, on some unimaginable scale, also play a role in stabilizing the vacuum itself? It's a wild, speculative leap, but it forces us to consider whether the universe's fragility might be intertwined with the presence of those who are here to witness it. This line of thinking, often called the participatory anthropic principle, suggests that observers are necessary to bring the universe into definite existence. In this view, the universe isn't a static, pre-recorded movie. It's more like a potentialities waiting for an audience to make it real. The unsettling quantum fluctuations that could spawn a vacuum decay bubble are just possibilities until they are actualized. Perhaps the continuous act of observation by conscious beings throughout the cosmos subtly suppresses these dangerous fluctuations, like a steady hand gently calming a turbulent sea of potentialities. Our very act of perceiving and measuring the world might be performing a silent, unconscious act of cosmic maintenance, holding the precarious quantum dice in a state that favors continued existence. This transforms our role from passive inhabitants to active participants, with our consciousness acting as a fundamental force that helps glue reality together. Of course, this is a highly controversial and philosophical interpretation, far from mainstream physics. The majority of physicists favor less mind-bending explanations for the measurement problem, like decoherence, which explains the collapse of quantum states through interaction with the environment, not consciousness. But the mere possibility highlights the deep, strange connections between the smallest quantum events and the largest cosmic structures. It suggests that the question of why we are here and the question of how long we will remain might be two sides of the same coin. Our existence may not just be a lucky accident in a stable universe, but a fundamental component of that very stability. The universe allows for observers, and in return, those observers might help keep the universe safe from its own inherent quantum chaos, at least for a while. It's a cosmic partnership of unimaginable depth, where the act of looking at the stars might, in some small way, be helping to keep them shining. This incredible idea, that our universe might be balancing on a knife's edge, leads us directly to one of the most profound theories in all of cosmology, the connection between the false vacuum and the very birth of everything. To understand this, we need to rewind the cosmic clock not just billions, but to the very first fraction of a second, to a time when the entire cosmos was smaller than a single atom. The prevailing theory for what happened in that first instant is called cosmic inflation, and it's here that the false vacuum plays the role of the ultimate creator. Inflation proposes that the universe underwent a period of exponentially rapid expansion, ballooning from a subatomic speck to something much larger than our entire observable universe in less than a trillionth of a second. This incredible burst wasn't driven by an explosion of matter, but by the energy stored in a field that filled all of space. Physicists call this the inflaton field. Now, think back to our metaphor of the energy landscape with its valleys and mountains. In its earliest state, this inflaton field was likely trapped in a high-energy false vacuum state. Picture a ball perched high up on a very flat, very high plateau. While sitting on that plateau, the field exerted a tremendous negative pressure on the fabric of spacetime itself, causing it to stretch at an unimaginable rate. This was the inflationary epoch. For a brief moment, the universe was this rapidly expanding false vacuum. But like all false vacuums, it was unstable. Through a process called quantum tunneling, or simply rolling down its energy landscape, this inflaton field eventually decayed. It found a path off that high plateau and tumbled down into a much lower, stable valley, the true vacuum we inhabit today. But here's the magical part. When that field decayed, it didn't just quietly settle down. The immense potential energy it had been storing during its time on that high plateau was released in a colossal flash, flooding the universe with a hot soup of particles and radiation. That moment of decay, that release of energy, was the Big Bang. The transition from a false vacuum to a true vacuum didn't end our universe. It literally created the one we live in. This means our entire cosmic history, from the formation of the first hydrogen atoms to the evolution of galaxies and life itself, is essentially the aftermath of a false vacuum decay event. We are not living in the remnants of an explosion, but in the energetic fallout from a cosmic phase transition, much like supercooled water finally freezing. Our universe is the bubble of true vacuum that formed within that raging sea of inflationary false vacuum. And according to the theory of eternal inflation, this process didn't just happen once to create our universe. That original inflating false vacuum background is likely still expanding elsewhere, and within it, countless other bubbles are constantly popping into existence, each one a new universe with its own Big Bang and potentially its own unique set of physical laws. In this breathtaking view, the same mechanism that could one day end our universe is also the very engine that brought it into being. So if this wave of transformation were to sweep through our region of space, what becomes of everything we know? not just the atoms and molecules, but the information they encode. Every book ever written, every historical record, every piece of music, the sum total of human consciousness and experience, and indeed all the knowledge accumulated by every civilization that might exist among the stars. This leads us to one of the most haunting questions in all of physics, the information paradox of vacuum decay. In our everyday world, information seems incredibly durable. We can burn a book, but in theory, if we could track every single atom and photon from the smoke and ash, we could reverse the process and reconstruct its pages. This principle that information is never truly lost but only transformed is a cornerstone of modern physics, but vacuum decay doesn't play by our rules. It isn't a rearrangement of particles, it's a complete rewrite of the rulebook that governs what particles are and how they can interact. Think of it like this: our universe operates on a specific operating system with set constants and laws. All of our information, from the data on a hard drive to the neural connections in your brain, is software running on that hardware. Vacuum decay wouldn't just corrupt the hard drive, it would instantly and permanently replace the entire operating system with a new one that doesn't recognize the old software, doesn't support its functions, and may not even have the concept of data as we understand it. The information stored in the structure of atoms, in the spin of electrons, and in the bonds between molecules would not be transferred or translated. It would be eradicated. The new state of the true vacuum would have its own fundamental constants. The strength of forces, the very concept of mass and charge, could be so different that the building blocks of matter as we know them cease to be possible. Protons and neutrons might instantly dissolve. Electrons could vanish or transform into entirely different entities. In this new reality, the intricate structures that held information, the precise sequence of bases in a DNA molecule, the magnetic domains on a hard drive platter, the delicate electrochemical patterns of a memory would have no equivalent. They would be not just destroyed, but made impossible. It would be like trying to play a vinyl record after melting it down and recasting it as a ceramic pot. The original information isn't just unreadable, the very medium for storing it is gone. This presents a profound challenge to some of our deepest held physical principles. The laws of quantum mechanics suggest that information must be conserved, that it can never be truly lost. Yet vacuum decay seems to present a scenario where that law is violently broken. Some theorists argue that the information isn't lost, but is instead scrambled and encoded into the boundary of the expanding bubble itself, the shockwave of changing physics. But this is a mathematical abstraction that offers little comfort. For any conceivable observer, either inside or outside the bubble, that information is permanently gone. Inside the bubble, the new laws of physics are so alien that the old information is not just inaccessible but fundamentally meaningless. Outside the bubble, the information is trapped behind a wall moving at light speed, forever out of reach. From any practical, experiential perspective, the erasure is total and absolute. This transforms the concept from a physical catastrophe into an ontological one. It's not merely the end of matter, but the end of meaning. Every human achievement, every struggle and triumph, every work of art and scientific discovery, every memory of love and loss, all of it would vanish without a trace, as if it never was. The universe would continue, but its history would be amputated. There would be no fossil record, no cosmic background radiation whispering tales of a previous state. No evidence that we or anyone else ever existed. It is the ultimate silent night, a forgetting on a scale so complete that not even the void would remember what was lost. This cosmic fragility leads us down a fascinating and speculative rabbit hole, one that connects the hardest of physics to the most mind-bending of philosophies, the simulation hypothesis. If our universe is, in fact, a sophisticated digital construct, an ancestor simulation run on some unfathomable computer in a base reality, then what does a phenomenon like false vacuum decay represent? Could it be less a natural law and more a feature or a bug in the code? From this perspective, the universe's foundational constants aren't laws of nature but programmed parameters. The specific value of the Higgs field, the strength of gravity, the mass of an electron, these aren't happy accidents of cosmic lottery. They are lines of code, the initial conditions set by the programmers. The false vacuum state, then, might not be a precarious valley in an energy landscape, but a temporary variable state within the simulation's architecture. It's a value that works, that allows for complex structures like galaxies and life to emerge, but one that isn't the program's most optimized or final setting. In this digital metaphor, vacuum decay takes on a terrifying new meaning. It might not be a quantum fluctuation, but a system event. The spontaneous formation of a true vacuum bubble could be the equivalent of a critical error propagating through the simulation's core processes. Perhaps it's a scheduled shutdown sequence, a planned reboot to clear the memory and initialize a new run with different parameters. Or maybe it's the ultimate blue screen of death, a fatal exception error from which the program cannot recover. The wave of change moving at light speed isn't a physical phenomenon, but the relentless advance of a termination signal, systematically wiping each sector of the simulation's memory and resetting it to its default null state. The reason we can't see it coming is the same reason a character in a video game can't see the player reaching for the power button. The shutdown operates on a level far above the simulated reality itself. This interpretation forces us to confront the nature of our own existence within such a model. If this is a simulation, then our consciousness, our memories, our entire lived experience, everything that feels profoundly real to us is simply data. The vacuum decay event in this context becomes the ultimate data deletion. It's not an explosion, it's a format command. The information paradox isn't a puzzle, it's a foregone conclusion. When you delete a file from a hard drive, the information isn't destroyed in a physical sense. The sectors of the disk are merely marked as available to be overwritten. The data becomes inaccessible from within the operating system's framework. Our universe's information wouldn't be lost to physics, but made irrelevant by a change in the higher-level programming. Our history, our art, our love, it all becomes stranded data in a deallocated sector, waiting to be overwritten by the next simulation's initial conditions. This fusion of ideas doesn't provide answers, but it radically reframes the questions. The existential dread of vacuum decay shifts from a fear of cosmic indifference to a fear of technological obsolescence or programmer intent. Are we in a stable, long-term simulation, or are we merely a temporary experiment, a one-off run destined to be concluded and erased? The unsettling unpredictability of the event mirrors the unpredictability of a user's actions on a computer. The program runs smoothly until suddenly it doesn't. This perspective offers a strange kind of solace, however. In a natural universe, the end is absolute and meaningless. In a simulation, an end could imply a transition, a return to some other state of existence, the base reality of the programmers. Of course, we have no way of knowing what that reality is like, or if our consciousness would in any way survive the transition. We are left staring into two different kinds of abyss, wondering which version of oblivion is more plausible and which is more terrifying. Confronting a concept as vast and impersonal as vacuum decay forces a profound psychological shift, a reckoning with our place in a cosmos that operates on scales and timelines utterly divorced from human experience. This knowledge isn't just another piece of scientific trivia. It's a fundamental challenge to our deepest instincts for safety, permanence, and meaning. On one hand, it can trigger a deep-seated existential anxiety, a form of cosmic dread known as existential risk awareness. This isn't the same as fearing a storm or a personal tragedy. It's the chilling realization that the entire stage upon which every human drama has ever played out could vanish in an instant without cause or warning, erasing every triumph and failure with perfect indifference. It can make our daily concerns feel trivial, even absurd, casting a shadow of pointlessness over our struggles and ambitions. This anxiety is unique because there is no one to blame, no system to fix, and no preparation to be made. It is the ultimate loss of control, and for some, that can be a paralyzing thought. Yet for many, this very same realization becomes a powerful catalyst for the opposite effect, a radical and profound appreciation for the present moment. The philosophical school of thought known as existentialism has long argued that confronting the reality of our own death is what gives life its urgency and value. Vacuum decay takes this idea to its absolute extreme. If our cosmic lease could be terminated at any second without notice, then the time we have is not just limited, it is infinitely precious. This awareness can shatter complacency and awaken an intense gratitude for the simple fact of existence. The warmth of the sun, the sound of laughter, the complexity of a thought. These are not mundane events but near miraculous fluctuations in a universe that could, at any moment, choose a different set of rules that doesn't allow for them. Knowledge of this fragility doesn't diminish our world. It makes every aspect of it shimmer with a startling and beautiful significance. It transforms our perspective from taking reality for granted to seeing it as a temporary or inspiring gift. This duality in how we process the information reflects a broader cultural divide in how societies handle existential threats. Some cultures, particularly those with a strong tradition of stoicism or cyclical views of time, might integrate this knowledge with a sense of cosmic acceptance. The idea of impermanence is not new. Many Eastern philosophies have long taught that all things are transient. The potential for vacuum decay could be seen as the ultimate expression of this truth, a reminder to practice non-attachment to a physical reality that was never permanent to begin with. The focus would shift from fearing the end to mastering one's inner response to it, cultivating a peace that is untouched by external circumstances, even the end of the universe itself. In contrast, more pragmatic, intervention-oriented cultures, often rooted in Western scientific traditions, might respond with a drive to overcome the threat. This mindset would reject passive acceptance and instead channel the anxiety into motivation for long-term survival. The conversation would quickly move from "what does this mean?" to "what can we do about it?" This could inspire monumental projects aimed at detection, prevention, or even escape, whether through cosmic engineering to stabilize the vacuum, or through the development of technologies that allow civilization to persist in some form beyond the death of our current universe. The psychological response here is not dread, but a defiant and ambitious curiosity, a refusal to let the universe have the final say without a fight. Ultimately, this knowledge serves as the ultimate mirror, reflecting back at us our own values and priorities. It asks us what matters most when literally everything is on the table. Does it drive us toward hedonism, a desperate pursuit of pleasure in the face of oblivion? Or does it inspire a deeper altruism, a desire to reduce suffering and create beauty and understanding while the window for such things remains open? The specter of vacuum decay, by presenting a threat against which no individual wealth or power is any defense, can ironically level the human playing field, highlighting our shared vulnerability and fostering a sense of global or even cosmic solidarity. We are all in this temporary bubble together. This shared precariousness might be the very thing that finally teaches us to appreciate our common home and our brief, spectacular moment in the sun. The very notion of an early warning system for such an event seems like a contradiction in terms, given that the threat itself moves at the ultimate speed limit of reality. Yet, the human intellect refuses to surrender to absolute fatalism, and scientists have devised several highly theoretical, albeit fantastically challenging, methods that could, in principle, offer a glimpse beyond the light-speed barrier. These aren't practical technologies we can build tomorrow. They are thought experiments that push our understanding of physics to its very breaking point, exploring the faintest of loopholes in the cosmic rulebook. One of the most intriguing ideas involves harnessing the so-called spooky action at a distance of quantum entanglement. In this bizarre quantum phenomenon, two particles can become linked or entangled, such that measuring the state of one instantly determines the state of the other, regardless of the distance separating them. This connection seems to operate faster than light, a fact that has been proven in countless experiments. Now, imagine a future civilization that develops the capability to create and maintain entangled pairs of particles on a monumental scale, placing one half of each pair on a distant space probe sent light years away from Earth and keeping the other half securely in a lab. The moment the probe is engulfed by an advancing vacuum decay bubble, the fundamental laws governing its half of the entangled pair would be instantly rewritten. According to the rules of quantum mechanics, this change should theoretically be communicated to its partner particle on Earth instantaneously, causing a detectable and catastrophic disruption in its quantum state. This would serve as a faster-than-light alarm bell, ringing at the exact moment the bubble reaches the probe, giving Earth a warning period equal to the travel time of that probe. If the probe were 10 light-years away, we would have 10 years of warning. The engineering challenges are, of course, beyond staggering. Maintaining quantum coherence over such vast distances and timescales is a problem we are nowhere near solving. But the principle offers a sliver of theoretical hope that physics itself might provide a way to peek around the corner of our own light cone. A less exotic but equally daunting approach would involve scanning the heavens for the faintest of echoes from the birth of a bubble. While the bubble's wall itself travels at light speed, the instant of its creation, the quantum tunneling event, might not be completely silent. Physicists speculate that such a fundamental phase transition of the universe could release an enormous burst of energy across a wide spectrum, a unique signature unlike any known astrophysical event like a supernova or gamma-ray burst. This would be the birth cry of a new reality. Our planet is constantly bathed in radiation from across the cosmos, and sophisticated observatories are always listening. If we were to detect an intense, point-like flash of energy that defies all known classifications, one that appears and then vanishes without any subsequent afterglow or remnant, it could be a candidate signal. The key would be in its uniqueness and its inexplicability. Furthermore, as this bubble expands, its leading edge, the wall of changing physics, might interact with the interstellar medium it passes through. This interaction could theoretically generate a specific type of shockwave or a shell of secondary radiation, perhaps observable as a strange, perfect circular anomaly in an otherwise normal region of space. Identifying such a structure would require a monumental and precise mapping of the entire sky, looking for these subtle, ghostly imprints that hint at a rewriting of the laws of nature happening just beyond the edge of our perception. Perhaps the most promising avenue lies in the detection of gravitational waves. These ripples in the fabric of space-time, first detected in 2015, are caused by the most cataclysmic events in the universe, like the merging of black holes. The formation of a true vacuum bubble would be the most cataclysmic event imaginable. The sudden, immense release of energy as the Higgs Field tumbles down its energy landscape would not just create light, it would violently shake the very foundations of space-time, generating a gravitational wave signal of unimaginable power. This wouldn't be the brief chirp of a black hole merger. It would be a singular, monumental burst, a cosmic thunderclap that would ring across the entire universe. Our current gravitational wave observatories like LIGO and Virgo are not sensitive enough to detect the specific frequencies such an event might produce, but next-generation instruments, perhaps based in space like the proposed Laser Interferometer Space Antenna or LISA, could be tuned to listen for these telltale tremors. A gravitational wave signal, by its very nature, carries information about the event that created it. A detection that matched the theoretical profile of a vacuum decay event would be the most terrifying and profound discovery in human history, a countdown clock etched into the fabric of reality itself. These methods all share a common thread. They are searches for the faintest whisper of an event that, by its nature, seeks to leave no trace. They represent humanity's unwavering desire to know its fate, to trade the terror of the unknown for the grim certainty of a countdown. Even a few moments of warning in the face of such absolute finality might be enough to fulfill our deepest need to bear witness to our own existence, to understand the universe even as it transforms around us into something unrecognizable. The pursuit of this knowledge is not about escape, but about the solemn, profound responsibility of consciousness itself to look into the abyss and seek to understand what it sees. This staggering possibility leads us directly to one of the most haunting questions in all of astronomy, the Fermi Paradox. If the universe is so vast and so old, with billions of planets that could support life, then where is everybody? Why does the cosmos seem so silent? The false vacuum theory offers a chillingly elegant and deeply unsettling potential solution. What if the reason we haven't found any evidence of other civilizations is because they are all inevitably silenced by the very process of their own advancement? Perhaps the ultimate existential risk for any intelligent species is not war or climate change, but the moment it gains the power to probe the deepest secrets of reality, and in doing so, inadvertently pulls the trigger on its own destruction. Imagine a civilization 1,000,000 years more advanced than our own. They have harnessed the energy of stars, mastered genetic engineering, and perhaps even achieved a form of immortality. Their thirst for knowledge is boundless, and their greatest scientists are dedicated to answering the most fundamental questions of existence. What are the true building blocks of the universe? Can the fundamental forces be unified? To answer these questions, they would need to conduct experiments of unimaginable scale and power, manipulating energies that dwarf anything found in nature. They might build particle accelerators that encircle entire stars, or create microscopic black holes in controlled labs to study the fabric of spacetime. And in one such grand experiment, in a quest for ultimate understanding, they might accidentally create the precise conditions needed to destabilize the false vacuum. A concentration of energy so immense, so perfectly configured, that it provides the critical nudge for the Higgs Field, creating that first fatal bubble of true vacuum. Their entire achievement, their entire history, would be erased in an instant along with their star system, and eventually their entire galaxy. This wouldn't be a malicious act, it would be a catastrophic, cosmic-scale accident. A mistake made in the pursuit of truth. In this dark resolution to the Fermi Paradox, the great silence isn't a sign that intelligent life is rare. It might be terrifyingly common. The silence could be the sound of graves, the aftermath of civilizations that reached a certain technological threshold, a great filter of their own making, and then vanished without a trace. The universe might be littered with the ghosts of species that looked too deeply into the abyss and caused it to look back. This transforms the cosmos from a hopeful arena of potential contact into a terrifyingly dangerous library of knowledge, where the most insightful books on the highest shelves are all booby-trapped. Reaching for them doesn't bring enlightenment, it brings annihilation. The reason we don't see any galactic empires or hear any signals could be that no civilization survives long enough to achieve them. They all hit this universal ceiling and are wiped out, their potential forever unfulfilled. This idea places humanity in a precarious and humbling position. Our own scientific trajectory, with our increasingly powerful particle colliders and our ambitions for even greater experiments, could be seen as us walking directly toward this same cliff edge. While our current machines are almost certainly harmless, the path we are on might one day lead to technologies that are not. The Fermi Paradox, viewed through this lens, becomes the universe's most severe warning sign. The silence is not an invitation, it's a cautionary tale. It suggests that the ultimate goal of a mature civilization may not be the relentless pursuit of greater power, but the profound wisdom to know when to stop, to recognize that some doors are better left unopened because what lies behind them could unravel reality itself. Our survival may depend not on how smart we can become, but on how wisely we choose to use that intelligence. Now, this is where things get truly mind-bending, because the propagation of this vacuum decay bubble isn't just a simple explosion in static space. It's an event unfolding within the dynamic fabric of spacetime itself, governed by Albert Einstein's theory of relativity. And relativity introduces a fascinating paradox. Time is not absolute. It flows at different rates for different observers depending on their speed and the strength of the gravitational field therein. This phenomenon, known as time dilation, could theoretically create bizarre and haunting scenarios where some pockets of reality might outlive the rest of the universe, witnessing its end from a unique and lonely vantage point. Imagine a future civilization that has achieved interstellar travel. They have a ship capable of cruising at an incredible fraction of the speed of light. According to Einstein's special relativity, for the astronauts on that ship, time would literally slow down relative to everyone else. A journey that takes them 10 years might see 50 years pass back on their home world. Now, let's say that while they are on their high-speed voyage, a vacuum decay event is triggered somewhere in the galaxy. The bubble begins expanding at light speed, erasing everything in its path. For those of us in a rest frame, living our lives at what we consider normal speed, the end would come suddenly and universally. But for the crew of that ship who are experiencing time more slowly, the approach of the bubble would appear to be delayed. From their perspective, they might watch from their windows as the universe around them seems to freeze and then wink out of existence star by star, while their own vessel continues on, temporarily isolated from the wave of change by the sheer distortion of time itself. They would be the last witnesses, living out their final moments in a bizarre slow-motion apocalypse, surviving for what might feel like years after the Earth and Sun were already gone. An even more extreme and dramatic scenario involves the ultimate cosmic tombs, black holes. These gravitational behemoths warp space-time so severely that time nearly grinds to a complete halt at their event horizons. To a distant observer, an object falling into a black hole appears to slow down, becoming redder and fainter, never quite crossing the threshold from our perspective. Now apply this to vacuum decay. Picture a lonely research station in a stable orbit just outside the event horizon of a supermassive black hole. The scientists on board are studying the extreme physics of gravity. When the vacuum decay bubble sweeps through their galaxy, it would eventually reach the black hole, but due to the incredible time dilation, the moment of the bubble's arrival at the station would be stretched out over what seems like an eternity. For the researchers, the end would not come in an instant. Instead, they might observe the universe beyond their orbit appear to speed up dramatically, stars fading and galaxies vanishing in a rapid blink, while the fatal wave itself seems to approach their station in extreme slow motion. They could potentially have generations of warning, watching the entire history of the cosmos play out its final act before the wave finally, inevitably, reached them. They would be the last conscious beings in the entire universe, living in a distorted pocket of space-time that temporarily shields them from the inevitable, providing a surreal and heartbreakingly gradual end. This isn't just theoretical poetry, it's a direct consequence of the equations. In the framework of relativity, the vacuum decay bubble expands along what's called a future light cone. This is a precise mathematical term that defines the boundary of all events that can be influenced by a single point in space-time. But for an observer moving at high velocity or deep within a gravity well, their perception of that light cone is warped. Their own personal timeline becomes desynchronized from the rest of the cosmos. This means that the absolute universal now that we intuitively believe in simply doesn't exist. The end of the universe is not a single moment in time. It's a complex surface that different observers would experience at different times according to their own clocks. For some, it's already over. For others, it is still an event far in their future, something they could, in principle, outrun or delay through relativistic effects, even if they could never truly escape it. This paints a picture of the apocalypse not as a single curtain falling on a stage, but as a wave of darkness that washes across the cosmic audience at slightly different times, leaving a few isolated souls in the front row to watch the rest of the theater go dark before the silence finally reaches them too. This staggering possibility that all of existence could be rewritten without cause or warning forces us to confront questions that go far beyond the equations of physics, reaching into the very heart of philosophy. If our universe is truly this fragile, a temporary arrangement of constants that could be revoked at any moment, what does that say about meaning itself? Does the potential for an arbitrary and total erasure render every human endeavor, every struggle and triumph, ultimately pointless? One perspective is that it renders everything absurd. This view, echoing the philosophy of existentialists like Albert Camus, suggests that in the face of a silent, indifferent cosmos that offers no reasons and can snuff itself out on a whim, our search for inherent purpose is a futile struggle against the void. From this angle, the universe is not just impersonal, it is fundamentally irrational. Our lives are like intricate sandcastles built with immense care on a beach, knowing that a wave we cannot see or predict will eventually wash them away without a trace. This cosmic absurdity can feel like the ultimate negation, suggesting that any meaning we find is a temporary illusion, a story we tell ourselves to distract from the underlying chaos. But there is another, far more powerful way to see it. This knowledge doesn't strip meaning from our lives. It places the responsibility for creating meaning squarely and magnificently upon our own shoulders. If the universe does not provide a built-in purpose, and if its continuity is not guaranteed, then the meaning of our existence is not something we discover out there in the cosmos. It is something we build right here in our relationships, our creations, and our experiences. The potential for oblivion doesn't make our actions meaningless, it makes them infinitely more precious. The warmth of a shared moment, the beauty of a piece of art, the pursuit of knowledge for its own sake. These things matter not in spite of the potential for vacuum decay, but because of it. Their value is not diminished by a distant end. It is intensified by the stunning, beautiful improbability that they are happening at all. We are not actors in a pre-written play whose ending gives the story its purpose. We are the authors writing the story ourselves, and the potential for the book to suddenly vanish makes every word we choose to write more significant. This shifts our focus from a cosmic scale to a human one. The question is no longer, what is the meaning of the universe, but what gives your life meaning today? The love you feel for your family, the satisfaction of mastering a skill, the awe of gazing at a starry night, these are not small things made insignificant by a vast cosmos. They are the very things that make the cosmos significant. They are the universe through the incredible accident of our consciousness, experiencing and valuing itself. A silent, empty universe has no meaning. A universe that contains beings who can wonder, create, and care is overflowing with it regardless of its ultimate duration. The fragility is not a verdict of pointlessness. It is a clarion call to pay attention, to be present, and to invest deeply in the only thing we know for certain exists, the present moment and our experience of it. This realization also challenges our deepest assumptions about legacy and permanence. We often strive to create things that will last, to build monuments and institutions that will endure for centuries. Vacuum decay presents the ultimate limit to that ambition, reminding us that on a long enough timeline, not even the pyramids, not even the works of Shakespeare, Not even the digital footprints of our entire civilization will survive. This isn't a reason for despair, but a profound liberation. It frees us from the anxiety of building for an eternal future that we cannot control and redirects our energy toward the quality of our present experience. The goal is not to create something that will last forever, but to create something that is truly valuable now. A life well lived is not measured by the duration of its echo in a universe that may one day forget its own laws, but by the depth and richness of its experience in the fleeting moment it is granted. In the end, the philosophy of vacuum decay brings us to a simple, powerful, and deeply human conclusion. The universe may be temporary, but that doesn't make our experience within it any less real. The potential for an end without reason doesn't invalidate the reasons we find to get up every day. In fact, it makes them all the more vital. We are presented with a cosmic choice. We can see the fragility as a reason to retreat into nihilism, or we can see it as the ultimate reason to embrace our humanity more fully, to be kinder, to be more curious, to love more deeply, and to find wonder in the astonishing fact that in a cosmos capable of such silent, instantaneous erasure, we are here at all, able to think these thoughts and feel these feelings. The meaning isn't out there, waiting to be found in the dust of distant galaxies. It's right here in the choices we make and the values we hold, in the temporary, beautiful, and defiant act of creating meaning in a universe that offers none on its own. Even if we accept the terrifying premise that our universe is fundamentally unstable, humanity's story might not end with a silent, instantaneous blink. Our greatest asset has always been our relentless ingenuity, our refusal to accept a fate written in the stars without first trying to rewrite it ourselves. So let's cast our minds far into the future, beyond the limits of our current technology, and imagine how a civilization that has mastered physics itself might confront this ultimate existential threat. The first and most crucial challenge would be detection. As we've discussed, a vacuum decay bubble expanding at light speed offers no conventional warning. But a sufficiently advanced society might not rely on conventional means. They could deploy a galaxy-spanning network of quantum-entangled sensors, placing sentinel probes thousands of light-years apart. The instant a probe is engulfed by the changing laws of a true vacuum, the quantum state of its paired particle in a central hub would be instantly disrupted, a faster-than-light alarm bell granting precious years or even centuries of advance warning based on the probe's distance. This wouldn't be a simple engineering feat. It would require maintaining quantum coherence across interstellar distances, a technology we can scarcely dream of. But it represents the first essential step, turning an unstoppable, invisible ambush into a known deadline, a countdown clock etched into the fabric of reality itself. With time bought through early warning, the next monumental task would be containment or prevention. How do you stop a process that rewrites the very rules of reality? You wouldn't fight the wave itself. That would be like trying to hold back the ocean with your hands. Instead, you would work to change the underlying cosmic landscape. The goal would be cosmic stabilization, gently massaging the Higgs field itself to eliminate the dangerous cliff edge, to transform our precarious false valley into the true global minimum of energy. The energy requirements for such vacuum engineering are literally astronomical, perhaps involving the coordinated energy output of multiple stars to generate counterfields that gently nudge the entire quantum field into a safer, more stable configuration. This wouldn't be a battle, it would be the most delicate surgery imaginable, performed on the patient of spacetime itself. It's the ultimate expression of a mature civilization's role, evolving from inhabitants of the universe to its stewards, actively maintaining the cosmic constants that allow for existence. But what if stabilization is impossible? What if the universe's fate is sealed? Then the only option is escape. Not escape to another planet or another star system, but escape from this universe altogether. This is where physics bleeds into the realm of science fiction, but the theories exist. One tantalizing possibility is the creation of a baby universe in a laboratory. Some models of inflation suggest that with an immense concentration of energy, we could theoretically pinch off a tiny region of spacetime, causing it to undergo its own Big Bang and inflate into a Chinese letter, separate universe with its own, potentially safer physical laws. We would essentially be cosmic parents, seeding a new reality and then finding a way to transfer our consciousness, our culture, and our biological essence into this new home before the old one is erased. The technological and ethical hurdles are beyond comprehension, but it represents our ultimate defiance against cosmic oblivion. A less drastic but equally fantastical method of escape could involve harnessing higher dimensions. If string theory is correct, our universe may be a three-dimensional brain floating in a higher dimensional bulk. A vacuum decay event might be confined to our specific brain. A far future civilization might develop the ability to project itself into this bulk, effectively stepping outside of our universe to watch the transformation from a safe distance, like moving from a room that's about to be renovated into the hallway outside. They could then potentially re-enter the new, stable universe that emerges from the decay, or perhaps travel to other parallel universes altogether. This wouldn't be survival for everyone. It would likely be a final, desperate exodus for a lucky few, carrying the entire history of humanity like a digital arc into an utterly unknown and alien reality. Perhaps the most poignant and arguably the most human response would not be escape but preservation. If we cannot save the universe, maybe we can save what made it meaningful. This would involve a project of staggering scale, the ultimate backup. A civilization facing its end might dedicate all its resources to encoding the sum total of its knowledge, art, history, and even the conscious patterns of its citizens into an indestructible format, perhaps information etched into the quantum spin of stable particles or encoded in a structure that could survive the transition between vacuum states. The hope would be that even if the laws of physics change, this cosmic message in a bottle might persist in some form, a fossil for whatever intelligence might emerge in the new universe to discover. It would be a declaration that our existence mattered, that we were here, and that we refused to vanish without leaving some trace, however faint, of our brief, beautiful moment in the sun. So where does this leave us, standing here in our temporary bubble of reality, contemplating a theory of our own potential erasure? The idea of vacuum decay is undeniably one of the most profound and unsettling existential threats we can conceive of. A silent, invisible end that could rewrite the universe without warning. It's a concept that stretches our understanding of physics and our place within the cosmos to its absolute limit. And yet, this knowledge doesn't have to be a source of paralyzing dread. In a strange and beautiful way, it can be the very thing that makes our existence feel more vivid, more precious, and more worth celebrating. Understanding this fragility is a kind of cosmic awakening. It forces us to recognize that the stable ground beneath our feet, the air we breathe, and the very laws of physics that allow for complex life are not a given. They are a spectacularly improbable and temporary arrangement. This isn't a reason to retreat from the world, but a powerful invitation to engage with it more deeply. That morning cup of coffee, the conversation with a friend, the wonder of looking up at the stars, these aren't mundane events. They are fleeting miracles happening against unimaginable odds. The potential for that silent blink doesn't diminish their value. It amplifies it, charging every moment with a profound significance we might otherwise overlook. This perspective also reframes our scientific journey. Our drive to understand the universe, to probe its deepest secrets with tools like the Large Hadron Collider, isn't a reckless temptation of fate. It is the most courageous and noble project a species can undertake. It is the act of turning on the lights in a dark and mysterious room, determined to see what's there, no matter what we might find. This pursuit of knowledge is our first and most crucial line of defense against the unknown. We investigate threats like vacuum decay not to frighten ourselves, but to one day perhaps understand them well enough to prevent them. Every calculation, every experiment, and every new discovery is a step toward securing our place in the cosmos, transforming us from passive passengers into active stewards of our incredible reality. The greatest takeaway from this entire exploration is not fear, but a renewed sense of privilege. The fact that we are here at all, that a universe of particles assembled into beings capable of contemplating its own beginning and its potential end, is the most astonishing story ever told. We are the universe becomes self-aware, looking back at itself and trying to understand its own nature. That is a breathtaking responsibility and a gift. So let this knowledge not be a weight but a liberation. Let it encourage us to live with more curiosity, more compassion, and more awe. Let it inspire us to support the scientific exploration that pushes the boundaries of knowledge, for it is only through understanding that we can hope to navigate the future. Our moment in the sun may be brief on a cosmic scale, but it is our moment, and that makes it worth cherishing, protecting, and experiencing to its absolute fullest.